Yes, sir. Okay, sir. Okay, sir. Sir, is screen visible, right? PPT. Okay, okay. So thank you. So I am Dr.V.M.Gaikwad, Assistant Professor working in Department of Physics, Amalakchand Mahavidyalaya, Yavatmal. And today I am going to present my recent research findings on design and investigation of structural, dielectric and electrical features of novel ferrite based composites. So this is the outline of my presentation. So basically, what are composites? Composites are nothing but the multiphase materials in which two or more different phases are present, and these phases are chemically distinct, but the interface separating between this constituent, it means that the interface is present in between two chemically distinct phases. Basically, on the basis of the preparation techniques, the composites can be classified into two broad categories: laminated type of composites and particulate type of composite. In particulate type of composite, one phase, it means the particle of one phase is embedded into the phase two particles, whereas in laminated type of composite, the one layer of particles of phase 1 is laminated over the layer of particles of the phase 2. So the question is, why composites are important? Because in composite there is an interface effect takes place, and due to that interface effect, enhancement in the properties as well as the modulation in effective material properties can be taken place. So the role of interfaces are very important, because across the interfaces rearrangement of chemical bonding, spin charge coupling, spin charge and orbital reconstruction, and modification of electronic properties and electronic structure takes place at the interface of the composite. That's why the composite materials are very useful and important. So in the current decade or in the current era, or in recently, designing and exploration of novel composite materials have been focused for the multiple technological application. And among these composite materials, ferrite based composite materials are well known for multiple applications in magnetic field, gas sensing field, microwave field, biomedical and clinical devices. Among those ferrite materials, zinc ferrite is very promising because it is lead free, it has a good excellent chemical and structural stability, as well as it has a moderate magnetization and significant dielectric constant. On the other hand, nickel oxide is also a promising candidate or promising compound, because it is also lead free, it has high moisture resistant, it has high thermal and chemical stability, as well as it has a wide band gap. Okay, with this motivation, we have motivated us to fabricate zinc ferrite and NiO composite and explore their structural dielectric and electrical behavior. So we have synthesized ZFO, that is zinc ferrite, by using chemical route, that is hydrothermal technique, and we have synthesized NiO by using co-precipitation method. And after synthesizing these single phase compounds, okay, both these compounds ZFO and NiO were mechanically ground in appropriate proportion and pressed into pellets, and these pellets were centered at 1000 degree for 4 hours for the proper interaction between those phases. Okay, and we have taken the weight ratio from 10 to 40% of NiO to prepare ZFO NiO composites. And the structural conformation was carried out by X-ray diffraction technique, and the XRD patterns of this ZFO indexed with the cubic structure with space group FD bar 3m, and the XRD patterns of NiO is indexed with the cubic structure with the space group FM bar 3m. The XRD patterns of composites shows both the existence of the peaks arising from ZFO and NiO. Okay, NO is the short abbreviation for nickel oxide. Okay, and other secondary, we have not found other secondary phases. It means that the phases structure, that is ZFO and NO phases, retain their structure in the composite samples. To get more insights into the structural aspects, we have refined the XRD data of those composite samples and NiO and ZFO samples by using readable refinement technique, using full proof software. and the refined data or the refined patterns of composite shows the peaks arising from ZFO and NIO phase both. And the secondary we didn't find any secondary phases. It means that our composite structure contains only two phases, ZFO and NIO. If you look at this magnified view of the reflection 400 and 200, we can say that this asterisk mark correspond to the ZFO phase, and this hash mark corresponds to NIO phase. If we see this, these are the peaks correspond to ZFO phase. As the NIO content in the composite increases, these peaks correspond to ZFO phase shifted to higher Bragg angle, whereas on the other hand, if we see the peak correspond to NIO sample in composite, this peak shifted towards the lower Bragg angle. This might be due to the interfacial strain induced at the interfaces of composites. It means that the grains, the interface between the grains of ZFO and NIO, the strain induced between them is responsible for this shifting, for this axidific shifting. Okay. Now we have extracted the structural parameters from this readable refinement result. As said that the peaks corresponds to ZFO phase shifted to the higher Bragg angle. It means that the clearly we have seen the increase in the lattice parameter with the NIO content. We have seen from this table or from this graph, decrease in the lattice parameter correspond to ZFO phase. In this graph, as the NIO content increases, the lattice parameter correspond to the ZFO phase decreases. This means that the contraction of unit cell of ZFO takes place in the composite. Okay, whereas on the other hand, we have seen in the previous this slide, the NIO peaks correspond to the composite sample shifted to lower Bragg angle. It means that the lattice parameter corresponds to NIO phase increases with increase the content of NIO in composite sample. And we have also obtained the phase percentage from readable refinement results, and we have seen that the we have found the observed phase percentage show good agreement which we have initially taken for the synthesis of these composite samples. And after readable refinement, we have obtained the CIF file, and this CIF file we have used to model the unit cell of ZFO and NIO. This ZFO unit cell shows the cubic structure, and it has two sides. One is octahedral site and other is tetrahedral sites, and at the octahedral site the Fe cation is present, or Fe cation is surrounded by 6 oxygen ions, and at the tetrahedral site zinc ions are present, and zinc ions are surrounded by 4 oxygen ions. And this is the NIO unit cell, and NIO unit cell contains NiO6 interconnected NiO6 octahedra. So with this unit cell modeling, after experimental results, we have extracted the bond length values from this unit cell, and we have seen from this table the bonds correspond to ZNO get compressed, and the bond correspond to the NIO get stretched, and this is because of the strain induced at the interfaces of NIO and ZFO grains in the composite sample. It means that it is the indication of structural distortion at the unit cell level after forming the composites. And this is the IR spectra of ZFO, NIO and composite sample. So this broad transmission peaks corresponds to stretching vibration of ZNO bonds in the tetrahedral site of ZFO sample, and this NIO, this is the transmission peak correspond to the NIO bond stretching vibration in NIO sample. And if you look at the IR spectra of the composite sample, so this IR spectra contains ZNO bonds, or the bonding vibration related to the ZNO bonds in the ZFO phase. It means that we have not seen any significant changes of bonding vibration, or no new bonding vibration appeared in the composite. It means that there is no structural modulation after inclusion of NIO phase in ZFO matrix. It confirms the structural stability of composite sample even after high temperature sintering. So these are the SEM images of ZFO, NIO and their composite samples sintered at high temperature, and we have seen that all the samples show dense structure with less porosity, and we have calculated the average grain size for ZFO sample. It was found to be 2.56 micrometer, and for NIO sample it was found to be 390 nanometer. And if you look at the microstructures of these composite samples, this sintered composite sample achieved better densification, which caused a good proper interaction between ZFO and NIO phases at the interfaces. And we have seen that NIO and ZFO grains are uniformly distributed throughout the composite samples. And to confirm the compositional analysis, we have carried out the EDAX, and we have seen that the EDAX spectra of this ZFO sample shows the elements that present in the ZFO compound Zn FeO. We have seen some gold signals because we have coated the samples with gold for the SEM imaging. That's why the gold signals came in this EDAX spectra. NIO sample contains NIO and oxygen with the weight ratio with the atomic ratio 1:1. If we see the EDAX spectra of the composite sample, this composite sample shows the presence of elements originating from both the phases, that is ZFO and NIO, and we have compared the observed weight percents with the calculated one, and it shows the good agreement with the observed values, and it means that the compositional analysis confirmed the expected stoichiometry in the composite samples. So this is the room temperature dielectric studies. Studies were carried out at the frequency range from 100 Hz to 1 megahertz, and we have seen the room temperature low frequency dielectric constant. We have seen large values corresponds to ZFO and NIO sample, but as soon as we made the composite, this dielectric constant values drastically decreases because this composite sample show low dielectric constant, since they are found to be more resistive. As this is the result from the conductive plot. The conductivity of the composite sample is lower than that of individual phases ZFO and NIO. And one important point in this dielectric plot, we have got less values of the dielectric loss of this composite at high frequency range, lesser than these individual phases. So it means that the loss get improved in the composite samples. So one more point I want to make here, that as soon as we increase the NIO content, the dielectric constant is also increasing. If we compare the 4 composite samples, earlier it was 1310 for 9010 samples, but as soon as the NIO content increases, these dielectric constant get increased. This is because as we increases the NIO grains, to number of interfaces corresponds to this composite are increasing in numbers. Okay, and because of that interfaces, some interfacial polarization, the values of interfacial polarization enhances. So that's why the NIO content will increase the dielectric constant values. And this is the electrical properties, and we have studied the electrical properties of composite sample by impedance spectra, and impedance spectra plotted in terms of Nyquist plots at room temperature from the frequency 100 Hz to 1 megahertz. And these impedance spectra of NIO samples are fitted with one semicircular arc, and this arc is the contribution of grain boundaries, and this contribution of grain cannot be seen here because of the low relaxation time of grain, which is out of measured frequency range. And composite spectra is 2 semicircular arcs, each one corresponds to grain and grain boundary effects, and as the content of NIO increases, the radius of this semicircular arc decreases, and composite samples are found to be more resistive than the individual phases. So these are our key results of electrical properties. So in conclusion, okay, I can conclude that we have synthesized successfully this NIO and ZFO composite by solid sintering route. It means that we have synthesized individual phases by chemical route, and then we have combined both the phases by solid state sintering route, and structural studies confirmed both the phases retain their respective structure without any impurities. And FTR spectra of composite sample shows no structural modulation after mixing the individual phases. FESM images shows different grain structure for the composite and individual because of the different thermal expansion coefficient as well as different rate of grain growth of ZFO and NIO phases in composite. And composite samples show significant dielectric constant with low loss. And we have studied complex impedance spectra of composite sample shows both the contribution from grain and grain boundaries, and they are found to be more resistive than individual phases. So thank you very much.